Hello everyone, and thank you very much for attending this presentation about the new equation-based method for parameter and state estimation of Modelica models. This work has been done with Hans Olsson, Audrey Jardin, Daniel Busquela, Eric Henningson, and myself, Luis Corona, in the frame of the Modeliscale project, and it is a result of the common work between Dassault Systèmes and EDF. For this presentation, I will first of all talk about the current implementation of initialization for Modelica models and explain why do we consider that it is important to introduce a new method for this parameter and state estimation. Then I will explain some principles of this new method and give some details about its practical implementation on a Dymola prototype. Afterwards, I will present some results of experimenting this new technique on a complex industrial model developed with the ThermoSys Pro Modelica library. And finally, I'll present some perspective of the work that I'm presenting. So, initialization of Modelica model is, of course, extremely important as for every model, but because it is necessary to correctly initialize a model in order to get accurate predictions by the model. So this is why we are very interested, and it's very important for us to correctly initialize the model. And by initialization, we mean that find an accurate initial state for the model. So by state we refer to the initial value of the dynamic states and as well to the values of the parameter. So usually this initialization in Modelica is done by inverse calculation, which means that we solve a square system in order to provide the values to these states. So when we need to have as many known variables as states to estimate. However, in general, the number of states to be estimated is much larger than the number of known variables. So it's necessary to do some arbitrary choices in order to fix some values, for example, in order to have a square system. But this means that this choice is arbitrary, and we don't know how this can affect the model. So that's why we are interested in data assimilation, which was developed in other fields of physics, like for weather forecast mainly, in which the idea is to use as much information as we have in order to give the best estimate of the real system. So that's why we have tried to develop to use this approach for the initialization of Modelica models because we are going to use all the available information about using the model, the knowledge that we have about the system, and of course measurements or observations that can be made on the real system if it exists, or on the operating point that we want if we are more in a design phase, for example. And so data simulation will give us the best estimation of the state and including as well an idea about the uncertainty related to this estimation. So it's very important this as well. This is the approach that we have implemented in Dymola, and to understand the principles of this method, well, there are different approaches, and I think that the best one to understand how it works is the so-called variational approach. And even if it can be a bit rough to start with this kind of equation, I think it's really the best way to do it, since here, if we understand this, in fact, this cost function, then we understand almost everything. So this is the cost function that we are trying to minimize in the frame of data assimilation. And here, in this function, this equation, what we have is several quadratic terms for several norms in which that define the problem that we want to solve, which means that here the x correspond to the tuners, that can be the initial state, the initial values of dynamic states or parameter values that we are trying to minimize, to find the optimal value. Then there are also here the p's, which correspond in a certain way to the same as the x, except that they depend on in the operating point. Yeah, that's why we are making here a difference, and there is a sum here over the number of operating points. Because sometimes, if we have we consider real measurements on a system, these measurements can be obtained in for different operating points. So it is important for us as well to take and to use all this information, and that's why we make the difference between the boundary conditions and the tuners themselves that are all the same for all the operating points. So maybe in an example it can be easier to understand. And then finally the last term is the y's corresponds to the observations or measurements and to the model output. So we're trying to minimize this difference. And in this cost function, the difference presented here for the tuners related to the initial value, the background value, etc., we have some covariance matrices that will give a different weight to this difference. So, for example, if we want to be close to the observations, we will give a high weight to this difference and this is done by giving a low uncertainty to this difference. But this we can see it better in the example. And of course, when we are minimizing this cost function, it's assuming that the Modelica model represented here by G is of course solved and correct. So that's the constraint. So we are simulating our model. So for the implementation of this new method, I think it's interesting to start from the user point of view, since we have in our requirements we wanted to make it easier for the user to use both the original model he has developed and the optimization model, so that there is not that much work to do, and both can be used for both normal simulation and optimization and the use of the data assimilation approach. So if we look at this example, for example, we have here a model, a Modelica model with some parameters, some variables, and the equations. And here we have the model that designed for the optimization, in which we are going to identify the parameters and which are the tuners, which here correspond to parameters like the k and delta p, and then as well the observations here, the observed. So in this case, we don't have a boundary condition, but it could be done as well. So and then with this record, in order we introduce these records to modify the variables, and we give the value and the uncertainty like this. So it's very easy for the user to identify these variables, and the initial model is not modified. And then this is for the physical model, but then the optimization algorithm, it is also very interesting to note the way it can be done in Dymola. So if you remember here, this is the cost function that we are minimizing, and for example, as you know, a necessary condition is that the derivatives are equal to zero. So we can just simply in Dymola set these derivatives to 0 and then use the Newton nonlinear system solver to just find this optimal state in a very simple way. And of course, we have implemented also other algorithms based on gradient descent, and this is very interesting to do directly in Dymola, since we can use analytical Jacobian, so analytical computation of the Jacobian, so the calculations are much faster. So finally, I would like to present some results of experimenting this method with a complex ThermoSys Pro model. So this is a model of a secondary circuit of a pressurized water reactor, and this kind of model is used at EDF for to compute the electric efficiency of the power plant. So of course, it's very important to have the best estimation of the initial state of this kind of model in order to ensure that the compute the we have a good insight of what's happening in the real plan. And for example, in this kind of models, we have over 2,000 parameters. So if we wanted to give the best estimation of these parameters by solving a square system, it would be very difficult. So it's necessary to make assumptions. But with data assimilation, it's possible to use all the knowledge we have and in the best possible way. So to find the best initial state. So for the example, we have consider a twin experiment, which means that the observations, measurements are obtained with the model itself. So by doing some simulation, then we get the result, and we use them as observation. And the goal this is obtained for a given state, and then the goal is to find again this state to see if the model, by data simulation it's possible to find again the state that was used to create this reference state, but starting from a different from a different one. So that's what we have tried to do. So producing with a reference state, so we given values for the tuner, 3 feet tuners and 2 boundary conditions. So, and this for 2 operating points. So we are going to see how the different operating points are obtained. For example, here in the nuclear power plant, this is as the thermal power. So there are differences because it's not always exactly the same. So it's important to take this into consideration. And then we look at 3 observations, 3 measurements. And these measurements are used as input for the data assimilation. So, and then we have considered 2 scenarios. So for both scenarios, we consider the main background. So as you see, for the tuners, we consider different values for the background as the reference states. So we are going to see if we are able to find them again or not. And then for the boundary conditions, we have the same, but this usually it can be measured. So we use them, and then in one case, we give very low uncertainty. So we are in scenario 1, so we are pretty confident on the value, and for scenario 2, we are not as confident. So the uncertainty is higher. And this is the values that appear in the covariance matrices. So, and if we look at the result, first of all, in both cases, the value of the cost function is is close to very low compared to the initial one. So the matching of the model outputs and of the measurement is very good. And then for the results for scenario 1, we see that we find values very close to the reference state. So that's good. And for the analysis, for the boundary conditions, I mean, also the values are very close and the confidence was very low. But in scenario 2, there are differences for the boundary conditions. We have not the same at all, and consequently the tuners are also different because they are compensating. But in both cases, the match between the model outputs and the measurements is very good. So finally, we can look as well as to the uncertainties related to to the estimated state, optimal state, and they are very close in both cases. So it means the model is giving a very good estimation through the measurement that we are using. And finally, I also compared to a previous implementation of a data assimilation that was done with ADAO, a Python toolbox that was using the model as a black box. Now we are having better computation times since we use analytical expressions for the Jacobian, and in addition, we are able to compute the uncertainties on the operating point, on the boundary condition, which was not possible before. So, as a conclusion, with the implementation of this new technique in a Dymola prototype showing that even complex model, the results are interesting, there is still work to do, and this technique in particular can be used as well for other purposes. So, even initialization model, failing models that cannot be initialized with the current initialization method, or the optimization algorithms can be improved, and we can use them as well in other optimization problems. And so there are many possibilities that can be explored. So that's all. Thank you very much for your attention, and we remain available if you have questions. Thank you very much.